Welcome, everyone. Thank you for joining us today for our mid-April working group meeting. I have to remind you that the meeting is being live streamed on YouTube and it's being recorded, and those recordings will be available later. Our speakers have very generously agreed to stay on for a half an hour after the end of the meeting for an informal discussion. And depending on how you feel about it, we'll either have a free-for-all in the main discussion room, or I've created some breakout sessions which we could use for individual discussions. As usual, I introduce myself, James Glazier, Reinhard Labenbacher, Jim Sluka, who's on the call, and Bruce Shapiro. And we're always available to take your suggestions, critiques, comments, and so on. So please feel free to talk to us. You've also seen this slide many, many times. We do have a Slack channel. We have a Twitter. We have our IMAG MSM wiki page, which always needs love and work. We now have a IMAG LinkedIn page, and we have a YouTube channel that archives all of our videos. And so we'd appreciate your help using these means of communication to get the word out. We also have a Facebook page. So people who are more savvy about social media than I am are would be much appreciated if they want to participate. Starting with a few weeks ago, we had the opportunity to have short announcements. Does anybody have a short announcement that they would like to make before we get to the main business of the meeting? I'm looking to see Jacob, go ahead.
Yeah, for those who contributed to the white paper of the integration and credibility reproducibility group, please vote. We have 2 votes currently, one from James, one from John. If you want a different venue, please vote. It's on our mailing list. Tonight, it's like in about 12 hours or 11 hours is the deadline to vote. Please vote.
Any other announcements? Well, I have one announcement, which is that we're going to have our annual CompuCell virtual tissue modeling course. We're going to be teaching it online. It will be the first week of August. We'll have 5 days of classes about how to build multiscale models, followed by a 2-day hackathon. That was a format that worked very well last year. Anybody who would like to learn how to build multiscale models in CompuCell would be welcome to participate. Over the years, we've had everything from high school students to emeritus professors and everything from pure mathematicians to surgeons take this class. So we'd love to have people join us. This year, there's also going to be a class the week before that on Paul Macklin's Physicell modeling methodology. And following tradition, the week before that, Herbert Sauer is going to be teaching ODE, reaction kinetic modeling and stochastic modeling using the Tellurium modeling package. So there are actually going to be 3 consecutive weeks of online tutorials and opportunities for people. We'd love to have your help getting the word out about these events. The other 2 will be announced more formally in the next week or 2. Any questions about that, please come to me, Jim Sluka, and if you go to the CompuCell 3D website, you can register and find out more information. As usual, we've got the request that if there's something good that's come out of this working group, you let us know about it so that we can document our successes and presumably improve. If you tell us about failures as well. And I'm not going to read the slide, you've seen it before, but anything that you feel is useful to document coming out of the working group would be much appreciated. Our schedule for upcoming meetings, I'm very excited that next week we have Deborah Peters from the USDA talking about predictive modeling in animal diseases. Very beautiful, very elaborate and extensive modeling with tremendous experimental validation. Donald Coombs is going to be talking about digital patient projects, so a very medical application. That's going to be very exciting. He's joining us this week on the call. We appreciate that. The following week, we have Penelope Morell and Catherine Morse. That's going to be interesting because they're very different topics. Penelope will undoubtedly be talking about unsolved problems in immunology. Catherine will be talking about standards and standards development from the point of view of somebody who's done that extremely successfully, not in particularly the context of biomedical modeling. And then going forward, you can see the schedule. As always, we would love to have your suggestions for future speakers. If you are a subgroup leader and you would like to present your successes or issues, we would very much appreciate you doing that. I also want to remind people who are subgroup leaders who feel they should be part of the steering committee that we have a steering committee meeting tomorrow morning at 11 a.m. If you need to have the link and you don't have it already, please contact Bruce or one of the other leadership for that. One of the things we're going to be talking about, I believe John Rice is going to be talking about organizing the next IMAG MSM PIs meeting and how that should be done. And that'll be exciting to hear about. As usual, during the meeting itself, because we're on a tight timeline, if there's time for questions, that's less of an issue now that we have the discussion group afterwards. We'd like to make sure that the questions are generic and short. I will give people a 5-minute warning. That is, after 15 minutes of your talk, I will break in and say, you have 5 minutes left, because it's hard to stay to 20 minutes. But we want to make sure that both speakers have able time to complete their full talks during the period that we have. So without more ado, I will turn the floor over to Winston, who is going to be telling us about a theory for multiscale modeling of disease dynamics. I guess if I could ask people to mute if you're not speaking, that would be very helpful. Winston, I'm going to stop my share and you have the floor.
Okay, so I can talk. Thank you very much for giving me the opportunity to speak to such a large group of people interested in multiscale modeling of infectious diseases. I have been working on this topic for some time now, I think since 2013. Apart from this theory, which I'm going to discuss with you, I've also developed some models and a method for integrating scales. But most of my work is about only integrating 2 scales. And so I'm going to share with you a theory that formalizes some of the knowledge about multiscale modeling of infectious diseases. I will have only about 4 segments of the presentation. I will discuss a little bit about what a theory is, and then I go into the theory and discuss some of the terminology that is used in multiscale modeling of infectious diseases. And of course, I will speak a little bit about the validation of the theory itself. So the word theory has everyday use and is also used in science. Well, in everyday use, it is taken to mean some guess that has no supporting evidence. But in science, it is a well-substantiated explanation of some natural worlds that might include laws and hypotheses. So then, as a result of that, a theory would be able to provide some basis for making predictions about what we observe. Now, there are different ways of developing a theory. If there is someone wants to give effort to developing a theory, 4 main approaches are useful for developing a theory. Maybe you might use one or a combination. So one of it is that you make observations. Maybe you have data that you have and you do some analysis of the data. And based on that data, you interpret it and analyze it and come up with theory to explain the data. or you might be extending or modifying an existing theory to explain new context, such as what might happen here, that we have already a transmission mechanism theory and we want to extend it to explain new phenomena about disease dynamics. Or you might be applying an existing theory into some entirely new discipline, and you have identified some similarities between the new discipline and the theory that exists in a totally different discipline. But also you might consider a combination of these, and I shall highlight how I have used a combination of these to come up with a theory, or the theory for multiscale modeling of infectious diseases. So based on these, a number of theories, some of these approaches, we can talk of information theory, Shannon, and game theory, John, and then we have a number of theories that have been developed to generalize or formalize knowledge that is already well known. We have relativity theories by Albert Einstein, and the theory of evolution by Charles Darwin. So in terms of infectious diseases, there has been very little development of theories of trying to explain disease dynamics. What has happened is that I've tried to look at it and identify that probably there are only two theories that have been developed in the past. One of them that has informed the modeling is the infectious disease causation theory. This is not a single theory, but a group of theories that were established and continuously refined to discuss the causes of infectious diseases. Of course, at the start, people didn't have much scientific knowledge and talked of the diseases as being caused by demons, and others may be saying that this is a punishment from God, up to the germ theory, when science begin to chip in to explain the causes of infectious diseases. And now we have the epidemiological triad theory, which is the final theory that we all agree that this is what causes infectious diseases. So, and it talks of interaction of host, pathogen, and the environment cause infectious diseases. Now, but then we also have the transmission mechanism theory. This theory highlights that transmission is the only main dynamic disease process that we have to incorporate in multiscale models of disease dynamics. And so at every level of an infectious disease that you want to develop a model, you just only incorporate transmission. And then this is normally done by, obviously, many people have done this by classifying either you are at tissue level or at cellular level, you just classify them into a number of homogeneous classes and you develop models to explain that. But then the actual transmission, the main mechanisms of transmission would be environmental transmission and direct transmission and vector-borne transmission. And these are the transmission mechanisms that have been incorporated into multiscale models, with transmission as the only main dynamic disease process. And this has happened for quite some time. With direct transmission, we have the famous SIR model and some variations of that. With environmental transmission, the only additional aspect is a variable that describes pathogen load in the environment. And vector-borne is a combination of those, except that you have two hosts, a vector host and a vertebrate host. Now, these ideas of transmission theory started off with Bernoulli and were continuously refined by Kermack and McKendrick into what we use these days, the SIR model and its extensions, including just a few aspects of it, but almost all of the mathematical biology has been based on this SIR model. Mathematical epidemiology has been based on this theory, transmission theory with the SIR model with a few extensions of it. But there's limitations to this theory, transmission mechanism theory, is that it is not capable of providing a systems level description of infectious diseases. And this is especially for processes of disease that happen at varying times and space. And so because of that, I also proposed this replication transmission relativity theory, which caters for both transmission and other processes that are relevant to disease dynamics. So transmission is just one process that happens in disease dynamics, but there's also pathogen replication or reproduction that leads to transmission. So because then we also have transmission and we have replication, that's why I called this new theory of disease dynamics the replication transmission relativity theory. But the relativity aspect I will explain shortly. Now, in a statement, this theory states that at every level of organization of an infectious disease system, there is no privileged or absolute scale which would determine disease dynamics. And you have to consider the interaction of both the microscale and the macroscale in developing models of disease dynamics. What it actually does is that this theory is that it acknowledges that at every level, both the macroscale and the macroscale, there are two different processes that influence each other in a positive, through a positive feedback mechanism. So at the microscale, that's where we normally have pathogen replication. And at the macroscale, that's where we have pathogen transmission. And these two processes influence each other in a positive feedback mechanism. The issue is that these two scales, what they do is that there's half a cycle which is about the transmission, and that happens in one scale. And then there's also another process at the microscale, which is replication. So you have a cycle which transcends which goes across two scales. And that will be a multi-scale cycle in disease dynamics. So when we are actually develop simple multi-scale models, we are considering this multi-scale cycle which goes across the microscale and the macroscale. So this theory, the relativity aspects, comes from the fact that it can be considered as an extension of relativity principle in physics, which states that there is no privileged frame of reference from which to determine motion of objects. That is when you are considering position or location, velocity, and acceleration, that these are relative. There's no absolute frame of reference from which you can consider these quantities. Now, this also can be, this relativity theory, replication transmission relativity theory, can also be considered as an extension if we then take the microscale and the macroscale as representing two different frames of reference. So this is basically the short of it about the theory itself for multiscale modeling of disease dynamics. But there's terminology that I've consistently used without giving explanations of it. So there are 5 terms that have a special meaning in this theory. It is the word system, subsystem, level, and scale, and component. what happens is that because a disease itself is a complex system, you have to bring down that complexity by decomposing it or discretizing it. And obviously from the complex system itself, the first discretization would give you subsystems, which are the three subsystems: the pathogen subsystem, the host subsystem, and the environment subsystem. And below that, you have the level, which is a level below a subsystem, and then we have a scale. But this definition is only applicable to the theory. You can't apply this discretization and the meaning of these words to all complex systems. Because of that, I have tried to, in order to accommodate these aspects, to say complex systems are of two different types. We have what are called functionally organized complex systems, and we have what are called the structurally organized complex systems. And structurally organized complex systems are the ones that can be considered under this consideration, where you have system, the whole complex system divided into subsystems, and then a level, and each level would have two scales in this context of structurally organized systems, where you have a microscale and a macroscale. So in this case, a level is considered a layer below a subsystem in the subpartitioning or in the hierarchy, and a scale is also considered a layer below a level. But so when you consider a subsystem or a level or a scale, you would say each of these is a component of an infectious disease system. Now, the most important aspect that is important for the theory is that where levels and scales are used in this partitioning of a disease system, levels are assumed to be loosely coupled, while scales, remember I said that each level has two scales, a microscale and a macroscale. So between the levels, there is loose coupling, but within each level, there's a strong coupling between the scales within a level. And this, because of this, we can analyze, because of this assumption, we can then analyze each level independently. So how do we, what are these levels that I've been talking about? This is just a summary of what I've been talking about, that we have subsystems, which is the pathogen subsystem, the host subsystem, and the environment subsystem. And when you consider the interaction of these subsystems, you then have about 7 main levels of organization of an infectious disease system, which run from the cell level, the tissue level, the organ level, and the micro ecosystem level. And this organ level can also be called the micro community level, because you can consider each organ as a community of pathogens. And then the micro ecosystem is when we consider that there is multiple infections among the micro communities. And then we have the host level, and then the community level. This is when you consider that the environment, the geographical environment is heterogeneous, and you therefore discretize it into various communities. Like you say that COVID transmission is different among the states, say, or among provinces, or among different cities. Then you discretize into various communities. So you have the community level. And the macro ecosystem level is when you have the different communities, but with multiple hosts and multiple pathogen infections. And as I've said earlier,
5 minutes.
All right, I think I'll be able to make it. Thank you. So this is the discretization I have been talking about, about an infectious disease system, which allows us to use that theory that you have these 7 main levels of organization. I'm not sure whether it's clear, but it is exactly what I have said, that you have the cell level, the tissue level, the organ level, micro ecosystem, all the way up to the macro ecosystem level. Now, you cannot consider the molecular level here, because what is happening at each level, these levels are considered the lowest discretization of a complex system, and each level exhibits the complexity. So it must have the 3 things that are involved in an infectious disease system. That is the pathogen, the host, and the environment are considered at each of these levels. So you can't go below the cell level. So then with this, we have 3 main levels, which we can group all those 7 levels because of the multiscale cycles that are involved into only 3 main levels. This is the primary level, which consists of the host level and its sub-levels. That is the cell level and the tissue level. And then you have the secondary level, which consists of the micro community and the macro community, and finally the tertiary level, where you consider the ecology and evolution of infectious diseases. Then with this, corresponding to those 3 main levels, you have different multiscale cycles with different structure. You have a primary multiscale cycle, which you have to consider when you do the modeling, and you have the secondary multiscale cycle, and you have the tertiary multiscale cycle. So it depends on the complexity that you want to incorporate in your multiscale model. But effectively, the simplest is where you have a primary multiscale cycle. And obviously, the most difficult is when you have tertiary multiscale cycle. Across these 3 main levels, I have worked to establish the main categories of multiscale models that can be developed. I'm not going, because of time, I'm not going to describe in detail how these different multiscale categories of multiscale models are different. But the first one, the individual-based multiscale modeling, is the simplest, and this is where most people who want to develop multiscale models do, because you don't explicitly incorporate the 2 scales that I have described to you. So it becomes the simplest. But these other 3 and going down are very difficult, and very few methods have been developed to develop multi-scale models in these other categories. So because of that, we can consider an infectious disease system as consisting of only 3 component subsystems, levels, and scales. This is in the context of, I know, because most of the definitions of multi-scale systems, particularly, have been informed by agent-based modeling, where they say it is consisting of a complex system consists of many interacting components, but this is not entirely true. It is just because of the method, which is agent-based, where there's several agents being incorporated into the model. But a complex system would have as simple as only these 3, say the host, pathogen, and the environment. But you also have this definition, which is based on properties of complex system, where you have openness of the system, the history of the system, and self-organization, which results in multi-scale and multi-level system. So I normally like to illustrate this complexity by a cartoon, by a story that I've read about the blind man and the elephant by John Saxon. This says that there were blind people who were asked to touch an elephant, and each touched their different parts. And when they were asked to describe what they see, they came up with different explanations of the elephant. And this is basically what happens when we do single scale modeling, that we are looking at a complex system and we don't incorporate the complementary information that comes from the different scales. that are involved in the complex system. So then, perhaps because there's no time, I just want to highlight that I have, using a method that I developed, tried to validate the theory, what I've done, because there's no time. This is a multiscale model for hookworm disease. Perhaps the two main points are this which is in bold, that is the linking from within host to between hosts. And the last one in equation 6, which also this first term, which also links the within hosts, and it scales down from between hosts to within hosts. So this method has been I've successfully used it to explain disease dynamics. What it does is that it actually gives you, when you work on it, the two reproductive numbers. And it's much simpler than the time since infection that is extensively used in multiscale modeling of infection. You actually get the two reproductive numbers, and you can see whether it is the replication, which is the reproductive number at the microscale, or it is transmission at the macroscale, which is contributing more to disease dynamics than the other. So this was the validation where we try to illustrate that even when you calculate the endemic equilibria, both the within host variables and the between host variables influence the same disease dynamics. So this is basically some numerical simulations to illustrate that. But this work I have presented is work of 4 main papers, which I have published over 4 years. So if I have left out any details, most of the information is in those 4 publications. They are general papers about multiscale modeling of infectious diseases. So thank you very much for listening to me, and I'll be available for further questions if you want clarifications at the end of the presentations. Thank you.
Thank you very much. We better move on quickly to Vivek, I think, and then come back for the questions at the end. That was still a very, very nice presentation. Thank you.